Okay, okay, let's start talking about homework number 6, and how to approach these types of problems, how to think of systems of reactions in series, reactions in parallel, and how to do the mixing strategies, etc. So let's start with these 4 problems right here. So in these problems, you're being told using separate feeds of A and B, sketch the contacting pattern and reactor conditions which would best promote the formation of product R for the following systems of elementary reactions. And I have A plus B goes to R, A plus A going to S for 7.2. So let's solve these problems right here. So this is the board. It's clear, and okay, let's start. So we're doing homework number 6, 10.4.2.2, and in problem 7.2. Problem 7.2 here. Calibrate this guy. Okay. So I have 2 reactions. I have A plus B going to R in addition to A going to S. And you're given 2 pieces of information. You're being told these are elementary reactions. And this means basically that the kinetics are the same as the stoichiometry, right? The second thing you're being told is that this happens in a flow system, right? Flow system. And these are all mentioned in last week's slides where we talked about, the mixing strategies in these types of systems, whether it's a flow system or a batch system. So the first thing, we want to maximize R, right? So the first thing we need to do is let's look at the reaction rates for both reactions. So for R1, the reaction rate will be K1, Ca, Cb. And for R2, the reaction rate will be K2, Ca. So if I want to maximize R, I want to maximize R1 compared to R2. So if I basically get this ratio R1 over R2, this is equal to K1 Ca Cb divided by K2 Ca. And as you can see here, the Ca's cancel out. So this is equal to K1 Cb over K2, right? Therefore, in order to maximize this ratio, I need to maximize Cb, right? I need Cb to be always high. And I need Ca to be low, right? So we maximize Cb and minimize Ca. So I want Cb to be high and Ca to be low. So in a flow system, the way to achieve this is, let's say you have your plug flow reactor, right? I'm going to introduce B in excess at the beginning, and then I'm going to introduce A in small amounts throughout the reactor, right? So this is your mixing strategy in a plug flow reactor or in a flow system. As a PF4, I'm going to introduce B at a high concentration. So this way the concentration of Cb is high. And I'm going to introduce A slowly at different parts of the reactor. This way the concentration of Ca is low. Okay, and this is the way to approach it. And these types of problems, we're not given any information about the activation energies. If you're given some information about the activation energies, you can also make a determination on temperature, as we mentioned in the last few slides as well, and in last week's lecture. Okay, so let me number this as 1, and let me save, and let's clear this. Let's move on to number 7.3. And in 7.3, the reactions, or I have 3 reactions in this case. I have A plus B going to R. I'm going to write K1. I have 2A going to S, and I have 2B going to T, right? These are the reactions in this problem, and let me just double check. Yep, A plus B going to R, 2A going to S, 2B going to T, and you're being told that this happens in a batch system. Okay, so how do we approach this? Again, I want to maximize R. So if I want to maximize R, I want to maximize this reaction and minimize these two reactions, right? Because I don't want my A and B, which are the reactants, to be eaten up in these reactions. So let's calculate or let's write the expressions for the reaction rates. So for R1, it will be K Ca Cb. For R2, it will be K Ca squared. For R3, sorry, K1 in this case, K2, and for R3, it will be K3 Cb squared. So if I want to maximize, R1 and minimize Ca and Cb, if you calculate the ratio of R1 compared to, for example, R2 plus R3, this is the ratio you're interested in, Kca Cb divided by, or K1 divided by K2 Ca squared plus K3 Cb squared. So in order to maximize this, I need Ca and Cb to be as low as possible, right? Because when these values are very low, I have a square effect here, so this ratio is going to be high. So in order to achieve this in a batch system, and this is in your slides as well, I'm going to slowly drip A and B into my batch reactor, right? So this is A, this is B. You can think of these as pipettes or maybe small feeding tank, whatever. And I'm slowly introducing A and B into the ideal batch reactor. And this way I'm gonna keep Ca and Cb low. So at no point will I have a very high concentration of A or B. And as well, Xa and Xb will be high, right? Because they're introduced in small amounts, they react immediately, so the conversion will be very high in this case. And this is really the mixing strategy you have to go for. Okay, let's move on. Let's have a look at 7.4. So in 7.4, the system you have is A plus B going to R, reaction rate K1 or first reaction. Second one is A going to S, and this one is in K2 or has a reaction rate of K2. And this time you're being told it's a batch system. And this is identical to 7.2, right? Yeah, this is the same as 7.2, except now I have a batch system. So again, I want to maximize the first reaction, minimize the second reaction. So R1 will be K1 Ca Cb, or 2 will be K2 Ca. So the ratio of these two guys, R1 over R2, will be K1 Ca Cb divided by K2 Ca. These guys cancel out, so I get K1 over K2 Cb. So in order to maximize this ratio, I need to maintain Cb to be as low as possible, right? Keep Cb low, right? Let's write it here. Keep Cb low. And in a batch system, the way to achieve this is, and again, this is in your slides, I'm going to start with only A in my batch reactor, and then I'm going to slowly introduce B, or this is actually B, Cb. I'm going to slowly introduce B into my system. This way, Ca is always very high, right? And Cb is always very low. Because, the amount of B compared to A will be very low, so the concentration of B will be very high. Oh, sorry. Okay, sorry. Let's pause for a second. I'm confusing my letters. Yeah, so I need to actually keep Cb high, right? This makes more sense than this. Because K1 over K2, in order to maximize this ratio, I need to maintain CB as high as possible. Yeah, I confused B and A in this case. Sorry about that. Just be careful. I need to keep CB as high as possible in order to maximize this ratio, right? So CB has to be as high as possible. In this case, so if I want to keep CB to be high and CA to be low, all I have to do is start with a reactor full of B. So I want to keep CB as high as possible and CA as low as possible. So I'm going to start with a system full of B, and I'm going to slowly drip A into the system. This way the concentration of B is always very high in this system, and having a high concentration of B is going to drive this ratio towards R1. So I'm going to get more of the product I'm interested in, which is R. Okay, so just be careful. I made a small error initially in this problem. So if you're still confused, please come see me in office hours. This is number 3. Let me save this slide. Let me clear out. Let's move on to number 7.5. Let's have a look at 7.5. In this case, I have A plus B going to R. I'm going to say K1. And then I have 2A going to S, K2. And you're being told this is done in a flow system, i.e. a PFR, right? Okay. Again, and I want to maximize the formation of R. So I want this reaction to proceed a lot faster than the second reaction, right? So let's write the reaction rates for these two reactions, right? So I have for R1, it's K1 Ca Cb. For R2, it's K2 Ca squared. So if I write the ratio, R1 over R2, it's going to be K Ca Cb over K2 Ca squared. And this is basically K1 over K2 multiplied by Cb over Ca. So in order to maximize this ratio, I want Cb to be high, and I want Ca to be low. And then I'm going to use the same strategy I used in 7.2 in order to achieve this in a PFR. The species which you want to keep at a high concentration, I'm going to introduce at a very high feed rate or a high concentration at the beginning of the reactor. And then the species with low concentration, I'm going to feed it very slowly at very low concentrations at different parts of the reactor, right? So here I'm feeding A. And this way the Ca will be low and the Cb will be high, right? So I'm introducing small amounts of A. Every time A is introduced, it gets completely reacted, gets completely eaten up. This way the concentration of A will always be low, and B is in excess. I'll have a huge amount of A throughout this reactor, so the concentration of B will always be high. This way this ratio will always be high, and I'm gonna push the reaction or push this ratio higher. This way I'm maximizing the production of R and getting very little S. All right, so these are the first 4 problems right here. Let me number this page. Let me clear. And let's go back to the homework, have a look at the second problem. Okay, let's have a look here. 7.6. So in this problem, you're being told that, and this type of problem is a new way of solve or a new approach. So just take note of the approach of how to solve these problems, 7.6 and 7.7, because these types of problems are going to show up on your test. Okay, this type of logic of solving problems. So you're being told substance A in a liquid reacts to produce R plus S as follows. A goes to R, A goes to S, so parallel reaction. We're going to feed with some concentration. Ca naught equals 1, Cr naught is 0, Cs naught equals 0. Enters 2 mixed flow reactors in series. Tau 1 is 2.5, tau 2 is 5 minutes. Knowing the composition of the first reactor, find the composition leaving the second reactor. Okay, so I have 2 CSTRs in series. I'm given the residence times, I'm given the initial concentration, the concentration between them, and I want to find the concentration leaving the second reactor. Let's go to the whiteboard here. Let's start working on this. Okay. So this is 7.6. So in this case, I have A going to R, going to S. You're being told it's an elementary reaction. So R, or the rate of formation of R, is equal to K1 Ca. Rs, which is the rate of formation of S, is equal to K2 Ca, and minus Ra, which is the rate of consumption of A, is just equal to K1 Ca plus K2 Ca, right? So these are the three reaction rates with respect to the three species. And now let's sketch what's going on. So in this case, I have two CSTRs. Then the feed from this guy. There's second CSTR here. And I'm given some information about the feed. So I'm being told that CA note is 1, CR note is 0, CAS note is 0, and here I'm being told CA1 is 0.4, CR1 is 0.4, CS1 is 0.2. The tau in this reactor is 2.5 minutes, and tau 1 and tau 2 in this reactor is 5 minutes, and I need to find basically CA2, CR2, and CS2, right? Okay, so how do I approach this? So what am I missing here? I'm missing the reaction rates, right? These seem to be a big thing. So the way to approach this problem is, again, I'm gonna look at the first CSTR. I have all the information here, and I'm gonna use this to get all the missing parameters, and then I'm gonna repeat the same thing with the second CSTR to determine the parameters which I'm looking for. So first of all, let's have a look at the performance equation for CSTRs. It's, with respect to A, it's tau over Ca naught is equal to Xa over minus Ra. And this is basically equal to Ca naught minus Ca over Ca naught multiplied by minus Ra is this expression, 1 over K1 Ca plus K2 Ca, right? And again, this is performance equation with respect to A. Similarly, I can write the performance equation tau over CR naught is equal to XR over minus R, right? And this is the same thing, except I'm writing it in terms of R. In this case, this will be CR naught minus CA over CR naught multiplied by minus 1 over K1 Ca. And be careful of this minus 1 because since R is a product, the reaction rate is K1 Ca, it's a positive. And here you must have a negative, so you get minus 1 over K1 Ca. Similarly, if I write it in terms of Cs or S, so I get tau over Cs naught is equal to XS over minus RS is equal to Cs naught minus, it has to be CR naught minus CR. Similarly, Cs naught minus Cs over Cs naught multiplied by minus 1 over K2 Ca. Okay, so these are my three performance equations for the system in terms of the three species, in terms of A, in terms of R, and in terms of S. Okay. So what do I want to find? Right, I want to find K1 and I want to find K2. These are really the missing parameters. So in order to do this, I'm going to use, and again, this approach, you use it for these types of problems, just learn the approach, try to understand it and apply it. So step 1, determine K1 and K2. And I'm going to use these two reactions. So writing the performance equation of R, it's going to be tau 1 over CR naught. This is equal to CR naught minus CR over CR naught multiplied by minus 1 over K1 CA. I'm going to cancel these guys. So basically, tau 1 will be equal to, and again, I'm going to use this minus to flip these two around, CR minus CR naught, or CR1 in this case, right? Because the output here, we're labeling it as CR1, divided by K1 CA1 as well, right? Because the output here is CA1. And I can use this equation to get K1 because, you know, tau, I know tau to be 2.5, right? CR1 is 0.4, CR0 is given to be 0, and CA1 is 0.4. So you can use this to calculate K1, and you're going to get K1 to be equal to 0.4, 1 over minute. You know, these are the units. Similarly, I'm going to apply the same thing for CS, for S, for, you know, using this second, the performance equation with respect to S to get K2. So basically, tau 1 is going to be equal to CS1 minus CS0 divided by K2 CA1. And again, similarly, this is 2.5, CS1 is 0.2, 0, CA1 is 0.4. And you can use this to get K2 equal to 0.2, 1 over minute. Okay, so now I have K1 and K2 for this problem. I'm going to use these two values to calculate CA2, CR2, and CS2, just using these equations, okay? So let me take a note here. Let me take a note here. So we calculated K1 and K2. So I have K1 equals 0.4, K2 equals 0.2, okay? And let's save. Erase these guys. Okay, here we go. Okay. Page number 6. Now I'm going to use K1 and K2 to get CA2, CR2, and CS2. So I'm going to use the first performance equation of A first. So now I have tau 2 is equal to CA naught minus CA over, or tau 2 actually, it will be, so CA naught, or the initial concentration into the second reactor, is CA1 minus CA2 divided by K1 CA2 plus K2 CA2. And tau 2 is given to be 5. So I have 5 is equal to CA1 is 0.4, 0.4 minus CA2 divided by 0.4 CA2 plus 0.2 CA2. And you can solve this to get CA2 equals to 0.1 mole per meter cubed. Verify this answer. Once you have CA2, you can get your CRs, again, using these performance equations. So similarly, using the R, or the performance equation in terms of R, I have tau 2. This is equal to, we said is equal to what? CR2 minus CR1 over K1 CA2. And if you plug in the numbers to solve for CR2, you're going to get CR2 to be equal to 0.6 mole per meter cubed. And similarly, you do the same thing for CS2. You're going to get CS2 is equal to 0.3 moles per meter cubed. Please try this. If you don't see it, send me an email or come to office hours. Okay, but this type of problem will show up on your test, 100%. Okay, let's save. Let me clear all the drawings. Let's go back to the homework. Okay, 7.7, again, similar type of problem. Substance A in the liquid phase produces R and S by the following reactions. Now you have a second order reaction, a first order reaction. The feed, you're given information about the feed, you're given information about the tau, and you're given some compositions for the species. Okay, let's go to the whiteboard and let's solve it again. It's an almost identical problem, except now I have a second order reaction in there. So my system in this case, so this is 7.7. I have A going to R, going to S, this is K1, this is K2. R is equal to K1 CA squared, right? This is given. RS is equal to K2 CA, and then minus RA will be K1 CA squared plus K2 CA. And again, it's a system of two CSTRs. And the feed in here is CA0 is 1, CR0 is 0, CS0 is 0. In this case, CA1 is 0.4, CR1 is 0.2, CS1 is 0.7, and I need to basically calculate CA2, CR2, and CS2, right? And again, for this type of system, your performance equation for a CSTR in terms of A, B, and C. So in terms of A, your performance equation will be XA over minus RA, and this will be basically, tau A over CA naught. So basically your tau will be equal to CA naught minus CA over K1 CA squared plus K2 CA. Verify that you're able to get this equation. Similarly for R, the tau will be equal to CR minus CR naught divided by K1 CA squared. And for S, your tau will be CS minus CS naught over K2 CA, right? So I have the taus in terms of, written in terms of all the three species. And again, similarly, we're going to do the same steps. So step 1, use CSTR1 to determine K1 and K2. And in this case, I'm just going to use, first of all, tau1 is equal to CR1 minus CR0 over K1 CA1 squared. I'm given the taus to be, so this tau is given to be 2.5, this tau is given to be 10. So this is equal to 2.5. CR1 I'm given to be 0.2. CR0 I'm given to be 0. Yeah, CS0 is given to be 0.3. 0 divided by K1. CA1 I'm also given, it's 0.4 squared. So in this system, I only have K1 missing. You calculate K1, you get K1 to be 0.5. Again, it's a second order reaction, so just write the units. Whatever it is, I think it's 1 over second meter to the 6 squared, right? Similarly, you can use the tau 1 for the S. So I get CS1 minus CS0 divided by K2 CA1, and this is equal to 10. And CS1 you're given to be 0.7, CS0 you're given to be 0.3, divided by K2, 0.4, and from this you can get K2 to be equal to 0.1, 1 over a minute. It's actually minute, because your taus are in minute. Okay. So now you have your K1 and your K2. Let's use them to get CA2, CR2, and CS2. I'm gonna erase this, guys. And it's the same approach, right? This is coming on your test. Know the approach, practice these problems. Make sure you're able to solve all of these things. If you're having a hard time, please come to office hours. Don't just show up on a test. I'm telling you it's coming. Don't just show up on a test not able to solve this problem, okay? Okay, so step 2. Will be to determine CA2, CR2, and CS2. So let's look at the tau. Let's look at tau2 in this case for species A. The tau2 will be CA1 minus CA2 divided by K1 CA2 squared plus K2 CA2, right? And this is equal to 10 minutes. And then if I plug in my numbers, I'll get CA1 is given to be 0.4. CA2 is what I'm trying to find. K1 we calculated was 0.5 CA2 squared plus 0.4 CA2. Okay, so this is a system I have. You're gonna cross multiply, you'll get a quadratic. So you're going to get basically 5 CA2 squared plus 5 CA2 minus 0.4 is equal to 0. And then you can use a calculator, you can use your delta to get the CA2, but the value for CA2 you're gonna get will be 0.0745 mole per meter cubed. If you forgot how to do a quadratic, remember how to do it, or find out how to do it using a calculator. This is very important. So once I have CA2, I can use the taus for the other species to get CR2 and CS2. So again, I can use tau2 for species R in this case. So this will be CR2 minus CR1 divided by K1 CA2 squared. And this is equal to 10. CR2 is what I'm looking for. CR1 I'm given, it's 0.2. K1 I calculated is 0.5. CA2 I just calculated here, 0.0745 squared. And you can use this to calculate the CR2 of 0.227 moles per meter cubed. You repeat the process for CS2, but using the performance equation of CS, and you should get a CS2 of 0.998 mole per meter cubed. Verify you're able to do this. If you're having a hard time, come to office hours and we'll do it together, okay? Save. Let me clear. Let's go back to homework and see what else is left. Okay, 7.8, 7.11. So in this case, you're given, let's see, what are you given? You're given a bunch of systems, right? You're given one system, A going to R going to S, again, parallel reactions. You're given the reaction rates for both of them. So for R, it's K1CA squared, you're given K1. For S, it's K2CA, you're given K2. You're being told the feed of aqueous A enters a reactor, decomposes, and a mixture of A, R, and S leave. And then you're being told to find CR and CS and tau for an XA equals 0.9 in a mixed flow reactor. 7.9, you have to repeat the same thing for a plug flow reactor. Okay, that's fine. Let's go to the whiteboard and let's solve these problems. I think it's page 9, right? So this is 7.8. So in this problem, I'm given a system A going to R, going to S. R is equal to K1CA squared. RS is equal to K2CA. You're being given K1 to be 0.4 and K2 being 2. Again, this second order, this first order. Just remember the units. This is your system basically. It's just a reactor, whatever it is. CA note is 40 moles per meter cubed, And here I have CA, CR, and CS. Okay, also, so for number 7.8, so again, this is the general thing for all the problems, but for 7.8 specifically, you're being told that XA is equal to 0.9, and it's being carried out in a CSTR. XA is 0.9, it's a CSTR reactor, and you need to find basically all the parameters, or you need to find CR, CS, and tau. So I need to find CR, CS, and tau. And you can, there are two ways to do it. You could use the selectivity, or what did we call it? Let me recall the exact term we used. You could use the fractional yield, which is the expression we introduced during lecture 7. And I highly recommend you use the fractional yield. It makes the algebra slightly easier when doing these problems. So if you recall from the slides, we said that CS is equal to phi of S over A multiplied by minus delta CA, where this expression here is your fractional yield, right? And again, phi of S over A is equal to dCS divided by dCr plus dCS, where dCS divided by dCA, whichever way you want to put it, but it's basically the reaction rate of the product you're looking for, K2CA divided by the reaction rate of the other species, or of all the other species. In this case, it's K1CA squared plus K2CA, right? So this is the fractional yield of S compared to A. So I have this expression, I'm gonna plug it in here, and minus delta CA, minus delta CA is just equal to CA naught minus CA, right? So if I combine these two guys and try to get CS, so in this case I have CS will be equal to K2CA divided by K1CA squared plus K2CA multiplied by CA naught minus CA. So I have K2, I have K1, I have CA naught. I'm missing CA, but I'm given a conversion, right? So to get CA, I'm going to use this conversion. XA is equal to CA naught minus CA over CA naught. CA naught is 40, XA is 0.9, so CA has to be 4, right? So CA is 4, basically 90% of this gets converted, so only 10% leaves. It's 4. Now I have all the numbers, I'm gonna plug them in, so it just becomes a cute calculation problem. 4K, 2 into 4 divided by 0.4 into 4 squared plus 2 into 4 multiplied by 40 minus 4. And you do this calculation, you're gonna get CS to be equal to 20 moles per meter cubed, right? So this is how you get the concentration of CS. And now to get the concentration of R, it's the same idea. To get the concentration of R, so to get the concentration for R, I'm going to use the same equation. In this case, I'm just going to put the parameters for R. So the fractional yield for R will be R over A. This will be dCr divided by dCr plus dCS. And in this case, dCr is the reaction rate for R, which is K1 CA squared. And now to get CR, I just plug in the parameters into this equation. And again, so CR, where the outlet concentration is equal to the fractional yield multiplied by the change in the reactant moles, right? So I'm gonna have CR is equal to K1 CA squared divided by K1 CA squared plus K2 CA multiplied by CA naught minus CA. I have all the parameters, so K1 is what? 0.4 CA1 squared is 4 squared divided by 0.4, 4 squared plus K2 is 2 into 4 multiplied by 40 minus 4. You do this calculation, you're going to get CR to be equal to 16 mole per meter cubed. Right? So I think we got everything this problem is asking for. It's asking for CR, CS, and tau. So yeah, you have all the concentrations, you can get tau easily, right? So tau in a CSDR, okay, let's write it here. So you said tau is XA, tau over CA, XA over minus RA, or you can do all the calculations. You can do it in terms of R, you can do it in terms of S. You can get the tau for this problem. Okay. So let's move on. Again, if you're having a hard time, please come to office hours. This type of problem will show up on the test 100% as well, right? So, you know, 2 problems which are going to show up on your next test. Be prepared, please. Okay, what's going on here? Some stuff